Hello guys, this is the 6th video of the series, Spectroscopy for Biologists. You may check the previous videos. The links will be kept in the description box. Now let's jump right in. Today we're diving into the fascinating world of IR spectroscopy. Get ready to explore the science behind this powerful technique. So, coming back to electromagnetic radiation, which spans from extremely high-energy gamma rays to low-energy radio waves, with infrared radiation falling between visible light and microwaves. The electromagnetic spectrum is classified based on the wavelength or frequency of the radiation. The IR spectrum refers explicitly to the portion of the spectrum with longer wavelengths and lower frequencies than visible light, but shorter wavelengths and higher frequencies than microwaves. IR spectroscopy examines the molecular vibrations to gain valuable knowledge about the structure and composition of molecules. It is commonly divided into three regions: near-infrared, mid-infrared, and far-infrared. To understand how IR spectroscopy works, we must grasp its fundamental principles. Molecules are like tiny vibrating springs, and their vibrations generate distinct energy patterns. We can unlock a wealth of information by examining the interaction between IR radiation and these vibrations. We know that atoms in a molecule are typically in continuous vibrational movement. And these atoms are connected by chemical bonds, which can be thought of as springs that allow the atoms to vibrate around their equilibrium positions. These vibrational motions involve the periodic stretching and bending of the bonds, resulting in the atoms oscillating back and forth. The equilibrium positions are the stable positions or locations where atoms in a molecule naturally rest or balance due to the attractive and repulsive forces between them. The more complex molecules show more complex vibrational movements. Infrared spectroscopy is a powerful analytical technique that identifies and analyzes chemical compounds based on their interaction with infrared light. It involves the interaction of matter with infrared radiation. IR radiation primarily induces vibrational and rotational motions of molecules rather than causing electron excitation or ionization. When infrared waves encounter a substance, they interact with the molecules differently. These interactions mainly involve vibrational and rotational motions. The substance can absorb, transmit, or reflect infrared waves. The absorption of specific infrared frequencies by a substance leads to generating an infrared spectrum. The infrared spectrum obtained from a sample provides valuable information about its molecular composition and structure. It reveals details about the molecular structure, functional groups, and chemical bonds present in the sample. By analyzing the infrared spectrum, scientists can identify the types of molecules present and gain insights into their arrangement and connectivity. So generally, molecules show two types of movement once they are induced by IR waves. 1. Stretching vibrations involve the rhythmic stretching and contracting of chemical bonds between atoms within a molecule. This movement occurs along the bond axis and changes bond length. Stretching vibrations can be classified into two subtypes: symmetric stretching and asymmetric stretching. In symmetric stretching, atoms on both sides of the bond move in the same direction simultaneously, while in asymmetric stretching, the atoms move in opposite directions. 2. Bending vibrations. Bending vibrations involve changes in the bond angles between atoms or groups of atoms, resulting in bending or angular deformation of the chemical bonds. There are multiple forms of bending vibrations, which can be either in plane or out of plane. In plane bending refers to the bending motion of atoms or groups of atoms within the molecular plane. It involves the movement of atoms closer together or farther apart while remaining in the same plane. In plane bending can be observed when there are bonds or groups of atoms that allow for such motion within the two-dimensional plane of the molecule. Scissoring is an in-plane bending motion where two atoms or groups of atoms move towards or away from each other within the molecular plane. It involves the scissor-like motion of the atoms or groups in the same plane. Rocking is also an in-plane bending motion where a group of atoms rocks back and forth within the molecular plane. It involves the swinging motion of the atoms or groups around an axis within the molecular plane. Out-of-plane bending, as the name suggests, involves the bending motion of atoms or groups of atoms out of the molecular plane. It results in the displacement of atoms perpendicular to the molecular plane. Out-of-plane bending typically occurs when there are flexible or rotatable groups that allow for such motion perpendicular to the molecular plane. Twisting. Twisting is an out-of-plane bending motion where groups of atoms rotate or twist around a particular axis perpendicular to the molecular plane. It results in the displacement of atoms out of the molecular plane. Wagging. Wagging is another out-of-plane bending motion where a group of atoms moves from side to side, resembling the wagging motion of a dog's tail. It involves the displacement of atoms perpendicular to the molecular plane. Stretching vibrations require higher energy compared to bending vibrations in molecules. This is because stretching involves changes in bond lengths, which typically have higher bond energies, while bending involves changes in bond angles, which have lower bond energies. Based on the nature of the sample of interest, we can use the different techniques of IR spectroscopy, transmittance spectroscopy. In this technique, a beam of infrared light is passed through the sample, and the transmitted light is detected. The resulting spectrum shows absorption peaks where the sample absorbs specific frequencies of infrared radiation. Reflectance spectroscopy. Instead of transmitting the light through the sample, this technique measures the intensity of light reflected from the surface of the sample. Reflectance spectroscopy is particularly useful for analyzing solid samples or surfaces that cannot be easily prepared as thin films. Attenuated total reflection (ATR) spectroscopy. ATR spectroscopy is used for analyzing samples that are difficult to prepare or handle, such as liquids, pastes, and powders. It involves placing the sample in direct contact with an ATR crystal, which allows for measuring the attenuated infrared light that interacts with the sample surface. That was everything for this video. In the following video, I will go through IR instrumentation. Thank you for watching.